pretty sure it's not water. I think it might be some kind of alcohol. What were you going to say? Kool-Aid? No, I don't think it's something we should. Even in an emergency, if you're really thirsty for Kool-Aid, I don't think you should break open the bird and drink. I think it's probably poisonous. We could look up what's in a drinking bird in a little while. But the drinking bird's head is covered with some kind of, I don't know, I almost want to say felt, but it's not really felt. It's some sort of kind of absorbent material that they've sprayed onto it or coated the glass. Bird's got a hollow glass head, and if you look closely, can you see the blue actually filling up the head? You see this growing inside there, and then it'll disappear as it runs back into the butt. Maybe if I turn on if I turn off the lights, then you can't see as well. But right up here, it should start getting darker. You can see it getting darker in the neck. So you can kind of tell if that red stuff weren't there, it would just, I think, be a clear glass ball, basically, that's hollow. And then the nose is just stuck on. I don't think that any of the liquid actually goes in the nose if you look at it. I'm going to pause the bird for a second and hold it up to the camera so you can get a better look at it. My little window's getting in the way. So you can see the tube is open right there. There's a little bit of space between the end of the bird's butt and the tube. And then there's that liquid. And I think this end, if I tip it upside down, you can see the liquid in the top of the bird's head. If I do this, all that liquid should go back into the butt, maybe. Uh-oh. Some of it's going to pour back into the head again. Kind of hard to control. So the question is, why does oh, and by the way, if I grab the bird's butt, watch what happens. Watch this liquid. Oh. See how fast it goes up into the head? But I don't have to grab its butt for this to work. It just works faster if I grab the bird's butt. Does anybody have any ideas about why this works? People at home, if you want to venture a guess, you can just raise your little artificial hand, like, oh, yeah. Anybody? Anybody have any idea how the bird works? It'll keep on drinking until it can't touch water anymore. If all this water was gone, eventually it would stop. And if I take away the water, it'll keep pretending to drink for a while. It just won't actually get anything. And eventually the head will become dry, and it'll stop doing this. So it's got to have some source of water for this to go on and on and on and on. And also for it to look like it's drinking. I don't know. I could just, after we're done talking about it here, I'll take the water away and we'll just see if it'll go all class. Oh yeah, it's just pecking at me. Yeah. So nobody has any ideas? So I'll have to start giving you hints then. I'm going to move myself over here. See if I can get to the right of the window. I can move the bird over, or maybe I can move this camera over. So many different ways to do this. There, do it like that. All right, so this is a pressure thing. And winds or anything move from high pressure to low pressure. We went over that yesterday. It doesn't have to be air for us to really be talking about pressure. I can put some pressure on this. Well, having trouble finding some space here. I'll just do this cup. So I've got this cup. If I push, I'm actually applying pressure to this side of the cup. And if I push on this side, I'm applying pressure to both sides. And if I apply enough pressure, I can squish it. But if I apply stronger pressure with this finger, and weaker pressure with that finger, and it goes this way. Now if I apply stronger pressure with this finger and weaker pressure with that finger, it goes that way. So back to the bird. This blue fluid is being pushed essentially up into the head of the bird again and again and again. So right now the thing that's making the fluid go up is the pressure is pushing the fluid up the tube. So where's there higher pressure? In the bird's butt or in the bird's head? In the butt? You think the bird has higher pressure in its butt, and that's why the fluid's being pushed toward the head? Gotta be. That's the way pressure works. If it's really pressure doing this, and pressure does a lot of things. We don't usually call it pressure. We just call it a push. But if it's getting pushed that way, that means there's higher pressure in the butt and lower pressure in the head. Now the question is, why is there higher pressure in the butt and why is there lower pressure in the head? We've been over this before a couple months ago when we were learning about when I had those questions for you about. So imagine that you have a sealed glass container like this, a jar, and you heat it up. What happens to the motion of the particles inside? What happens to the temperature? What happens to the pressure? And then I would ask you questions like, what happens if you, oh, I don't have a bag, but if I had a bag that was sort of flexible, what would happen then? What would happen to the volume and the temperature and the pressure? So, answer this, now that you probably erased everything I just said from your memory banks. The pressure in the head, if we had to label it high or low, what would we call it? High or low? Low. And the pressure in the butt is high. Now, I found my jar that I was looking for last class that I have pressure things in. Got suction cups, but right now I just want it as a jar. If I want to increase the pressure inside this jar, just using temperature, what do I do? If I want more pressure in the jar, do I heat it up or cool it off? Which one's going to make more pressure? Heat it up. And do you remember why? Why does heating make more pressure? Does anybody at home remember? If I heat this jar up, why is it going to have more pressure in it? Anyone want to? Anna?
Because the molecules are going to start to move faster.
And when they do, they're going to hit the sides of the jar and they're going to push out harder. So if I put this in hot water, if I put it, I don't know, in an oven, the particles, the air particles, molecules are going to bounce around and they're going to push against the walls harder. And then if this were a flexible container, it would start to bulge out and maybe even explode if I heated them up enough. That's what happens in most bombs. There's just really rapid heating and expansion and pressure building up until it explodes. So now if I wanted to make low pressure in here, what would I do? Heat it or cool it? Cool it. And the opposite would happen. Those particles that are moving around real fast, they'd slow down, they'd stop pushing against the walls, and if this were flexible, it would shrink. But if it's solid, the pressure would just decrease. So, based on that, what's hotter, the bird's butt or the bird's head? The bird's butt. So you just said the bird has a hot butt, right? Can I like go on record that somebody just said the bird has a hot butt? So yes, compared to the head, the bird's butt is hot, and the head is cool. Now, what's making the bird's head cool? The water. So if you take a shower in the morning and you get out of the shower and you don't dry off right away, you just leave yourself wet, you feel really cold. And it's because, we haven't gotten into this, but evaporation, when that water on the bird's head turns from a liquid to a gas, does turning from a liquid to a gas require you to lose energy or gain energy? Do you need to, if I'm a liquid molecule like that water and I want to start flying away, do I need to lose energy or gain energy to turn into a gas? Anyone? Anybody feel confident in your answer? Like, gas molecules are flying around in the room. Liquid molecules are sort of slithering around in my beaker. Which has more energy, a gas or a liquid? Anybody from home? We haven't been over this in a while, and we never really studied phases of matter, but we kind of did. Oh, I guess I could draw it here. This is, if I just draw little particles of solid, they just sit here. These would be individual atoms, something like neon. It's a solid. They sit there in place, and they maybe kind of move around like this and jiggle, but they don't actually move. And then if you have a liquid, in my diagram here, it kind of looks like a solid, but if this turned to a liquid, these would start to move around, and they would settle out, and they'd move all over, but they wouldn't fly. And then if we turn this into a gas, some of these would just start flying away, and they'd be flying all around. They'd leave the container like that. So this is least energy, or I could call this coldest, and this is hottest. This isn't what a water molecule looks like, but if you imagine a solid like ice, you heat it up, it starts to melt and flow around a little bit, heat it up a little bit more, and it flies away. So what I'm trying to get you to say, see if you can say it now. In order for the liquid that's on the bird's head to evaporate and turn into a gas, oh, I guess you couldn't actually see what I was drawing there when I drew my gas. For it to evaporate and turn into a gas, does it need to gain energy or lose energy? Gain. And so what happens with sweating, the reason we sweat and the reason you feel cold when you have water on you is that water is evaporating from the bird's head, it's turning into a gas, it needs energy to do that, and it takes it from the bird. And when you take energy from the bird gets cold. So if I put some water on my finger and wave it around in the air, it feels cold because that water is evaporating, it's turning from liquid to a gas, it needs energy to do that, it takes it from me. But I guess you don't really need to understand that to understand that when you're wet it feels cold, right? You get out of a swimming pool, if it's windy, you're particularly cold. So that's why the head is cold. And the butt, nothing's really making the butt hot. But what will make the butt hot, I'll do it in a second. What am I about to do to heat up the butt? What am I going to do to the already hot butt that the bird has to make it even hotter? I'm going to grab its butt. Okay, so watch see the liquid just shoot right up immediately when I grab the butt? That makes the butt even hotter. So the butt's actually room temperature, and the head is a little cold because it's wet. So we've got higher pressure in the bottom from just it being warmer, and we've got lower pressure in the top from it being colder, and the liquid gets pushed up every time. And then when it does this, when it tips like this, I've shown you this before, that hole right there opens up, and that allows the pressures to equalize. It's like opening up a balloon and letting the air go wherever it wants. So the higher pressure in the butt and the lower pressure in the head, they just mix. So they go back to being even again. But then as the bird starts swinging its head around, that cools the head off more, drops the pressure in the head, and makes the water move up. So if I had to summarize the most important things going on here, I would say that it's this is actually going to be this is a good demonstration for what we're going into, but it's also kind of bad. And maybe later, if I remember to clarify what I mean by that, I will. But this is supposed to show you that things move from high pressure to low. And it's also supposed to show you that pressure can be influenced by temperature. But the pressure and temperature thing is going to be a little bit different than what we're doing today. I'm going to put the bird away. High pressure to low pressure. Just don't forget that. That's the most important thing. Did you make that yourself? No, you can buy those. If you want your own drinking bird, you can get them all over the place. They're a really common science gadget. Just Google drinking bird. Uh-oh. In order to show the drinking bird, I got my camera all changed around, so it may take me a second to get it right. The plan for today is to take up where we left off and get through these. And then tomorrow at our meet, I'm going to be informally quizzing some of you. So I'm going to be putting you on the spot and asking you some questions from these notes. And not going to affect your grade, but of course, when you're put on the spot, you want to be able to answer the questions. So your job tonight is to go over this whole handout and review it. And there's nothing on the handout because we were working on another sheet, which makes this perfect for studying. Oh, by the way, before I move on too far, I wanted to show you something. These are the first few 3D printed snowflakes. I'm pretty sure that one's Elijah's. And I think this one's Anna's. And then I think one of these is, I think maybe this is Quinn's. And I think maybe this is, I don't know. This might be Alyssa's. Or maybe that's Harriet's. That might be Harriet's. We'll figure it out later. But anyway, I've got 4 more ready to go and then 1 more after that. So if you haven't put your snowflake design in the Google Drive folder, make sure you do that, and also email me just to let me know that you did it, because as far as I know, I've gotten all the designs out of there, and there are just 5 more to do. And Jace's looks a little different. He wanted a keychain. See if I can show you that.
Is that 3D printed?
Yeah, 3D printed. So his is a little bit smaller, but he wanted a keychain version, so I put a little handle on his to make a keychain. And I guess if anybody wants that, just let me know. Although these are already done, so these are what they are. But there are 5 done and 5 more to go. And I think there are 16 or 17 of you, so 6 or 7 people haven't given me anything.
So you just design it and put it in the Google Drive?
Yeah. Yeah. All right, back to here. We left off with number 13. So this is where we were talking about ears and the effect of air pressure and changing air pressure on ears. So maybe I should just sort of quickly review my notes. This is showing a balloon, and it's showing pressure moving from high to low. And number 3 is just saying that moving air, another name for that is wind. Air moves from high to low pressure. Number 5 is super important. If I were to ask you what causes wind and what determines the direction that it goes, you could say wind is caused by pressure differences in air pressure, and it blows from high pressure to low. And there was this picture showing how if there's low pressure here and high pressure there, the wind's going to blow like that. And then we got into atmospheric pressure, which is, it's not like pressure in a jar. Don't think of the atmosphere as a sealed jar, really. The air in this jar has nowhere else to go. But if we heat up the air in the atmosphere, it can just go as far out as it wants. There's no real lid on the atmosphere. So atmospheric pressure is caused by the weight of air on top of us. In this picture, this is water pressure. So I was just showing all these buckets of water on top of somebody, which is why your ears hurt when you go down deep underwater, because there's a lot of weight on you. And in the next page, I was just confirming that air has weight. We know that because it's got mass, and anything that has mass has weight, but also a balloon went from 3 grams to 3.5 grams when I inflated it. So air has weight. And this is showing that somebody who's down at the bottom of a mountain experiences the strongest air pressure because they've got the most air on top of them. And it may not seem like air is very heavy. If you just kind of do this, it doesn't feel heavy, but it adds up. We've got miles and miles and miles of it on top of you. And it actually, if you could weigh it, first of all, when you're underwater, like if this is you standing at the bottom of a pool, do you feel heavy underwater? No. You still have weight. Gravity's still pulling you down. It's just that there's this concept called buoyancy we're going to talk about in a minute that makes you feel lighter. So if you pick up a big heavy rock on the bottom of Indian Brook and you lift it up underwater, it doesn't feel very heavy until you get it to the surface. So when you're weighing stuff in a fluid, those things don't always feel heavy. Like the air around us doesn't feel heavy because we're in the air. Just like the water around you in a pool wouldn't feel heavy if you did this because you're in the water. So I guess what I'm saying is the air doesn't feel heavy, but it actually kind of is. And 13, here was the eardrums. So 14. We're close to sea level. At sea level, the weight of air above us creates an average air pressure of, so 14, average air pressure. Oh, if you want another sheet of paper, there's some right there. At sea level equals 14.7 psi. And the next thing is asking what psi stands for. Does anybody know the P?
Pressure per square inch.
The square inches is right. This is square, and this is inch. Does anybody at home know what the P is in psi? It's not pressure per square inch. It's not per, something else. It's a unit of force. It's the unit of force we use, pounds per square inch. Pounds per square inch. And I always do this about this time. I'm going to try to give myself a square inch tattoo, approximately a square inch. There, that's something like a square inch. You can see it on here. It's not very big, but what I'm saying is there are 14 pounds of force from the air pushing on my skin right there. Does it look like it? It doesn't. You probably don't think of any force pushing on you at all. If you try to think of something that's 14 pounds, the first thing that comes to mind is a heavy bowling ball. If anybody goes bowling, do any of you use 14-pound balls? Or you use 12 or 10 or 9 or 8? So 14-pounder, those are the heavy ones. Just imagine that bowling ball pushing against my skin. And we don't feel it for a lot of reasons. Partly because it's spread out evenly, partly because we have pressure in us. But it's there. So that's number 14 and 15. And 16, get on my suction cup. I found my suction cups. So there's a suction cup. Now I could just be pretending here, but I'm not. This suction cup's strong enough to lift up a desk. I don't know. Do you think it'll work on the bottom of this jar? No, it doesn't. It's got to be something where it gets a good seal. This is actually cool. Somebody discovered a few years ago that if you stick a suction cup through a piece of paper, it still sticks to the table. Now you can slide it this way, but to pull it straight out is kind of hard. And normally I pass these around. I guess I've only got this one. I don't know if I should pass them around today, but I won't for now. Maybe I will later. So the question is, explain how or why, or explain/show why a suction cup sticks to a glass surface and why a ball doesn't. So this mouse, for example, it's not a ball, and my hand is not a ball, but none of them stick to the surface. I mean, nothing's sticking here except this suction cup. And this suction cup only sticks if I do what? It's not sticking now. Yeah, I've got to push it down. And there's actually, see these little nubbins on here? You know what they're for? If I squeeze them in, then I can just lift it up. And maybe that would be worth looking at from the side. So here, if I just gently set this down, it doesn't stick. If I press it down tightly, then it really sticks. And these little nubbins right here, if I do this, then it comes right up. Now I can slide it this way, but I just can't lift it that way. Somewhere around 40 or 50 pounds of force it takes to lift this thing up, unless I do it the easy way. So I want to draw a picture. Oh, I guess I need to switch to my paper because I'm not drawing on this one. Nobody at home has this, and if I draw on it, then I can't use it to quiz myself. So I want to draw a picture showing why this sticks and why that doesn't. It doesn't have to be a ball, could be a hand, could be anything. By the way, this was 14 and 15 because I did the pounds per square inch there. So I'm just going to redraw this. This is the glass. Here's the suction cup. Might as well use the same piece of glass, and here's the ball. All right. I want to draw the pressure pushing on these things. I'm not going to draw, actually I'll maybe draw the ball. I'm going to do a good job on this ball. Here's the glass. Is there air right over here pushing on the ball? Oh, you know what? Hold on for a second. Let's come back to that. I want to show you the next thing, because there's something crucial that I haven't really revealed to you. Alright, so now I'm going to maybe make a mess. Hopefully not. But if I do, you'll all love it. So there's nothing to be lost here. I'm going to fill this up. I've stolen this. Don't tell Mrs. Vinsel, but I took one of her nice transparency sheets and I cut it into little pieces. And there really aren't a lot left. It's because I couldn't find my own. I used to have these laminated pieces of paper, but I couldn't find them yesterday, so I cut up one of her transparency sheets. Alright, so what I'm going to do is fill this with water. Or maybe not fill it, maybe I'll just do it about halfway. And I have taken precautions of taking most of the cleaning stuff out of the sink. Just going to put this on top. Anybody ever seen somebody do this?
I have.
Okay, I'm going to turn this over. And I could do this right on top of my notes. Yeah, that's more exciting if I do that. Maybe I'll do it over I'm not going to do it over the remote. So now I'm just going to let go. There was a little tiny droplet there. So I'll do it over the sink a little bit more. I can be crazy over the sink. I can do this. And just to show you, it's not really even very well attached. I don't know if I can, good thing I didn't do that over the computer. But the most important thing that I'm showing you here, and the reason I wanted to do this before we did the diagram with the suction cup and the ball, is can air pressure push upward? Yes, that's why this can happen. The thing that's holding the water in is the air pressure pushing up from the bottom here. If we pumped all the air out of the room and the air that's pushing up right here went away, then all this water would fall out. So right now there's a pressure difference. This is actually a pretty complicated thing. The pressure in the room is pushing up harder than the pressure in that jar is pushing down. And the reason is, when I put this on and I let go, all the water starts to fall a little bit. And when it falls, it stretches out the air in the container. So if you compress air, you make it higher pressure. If you stretch air, you make it lower pressure. So there's low pressure pushing down difference is enough to hold up this water. So the purpose of that, we'll come back to that in a second. The purpose of that was just to get you convinced that air pressure can come from every direction. So if I want to draw all the air pressure pushing on this ball, I need to draw it from all sides. So there's some air pressure. Even underneath, there's air all around us. And if you want to get rid of all the air around you, you have to work really hard to do that. You have to build some kind of special device that excludes the air and won't let it back in. Anybody think of a special device that pushes the air out and won't let it back in? Or something that's maybe on the screen here? Suction cup. So if I push this down, the air that's underneath it gets pushed out, and then it can't get back in again unless I pull up really hard or I lift up the edges so that the air can squirt back in. So this suction cup has air pushing like this. Is there any air underneath it? Not if you do it right. Not if you squeeze this down to the surface. You squish out all that air. So this has air pushing from both sides. This has air pushing from one side. So I'm going to make a little note that says there's no air beneath suction cup. So air pressure should be two words. Kind of looks like I wrote it as one word. Air pressure only pushes it toward the surface. So it sticks. And in the case of the ball, the air pressure is pushing it in every direction, so all this kind of cancels out. In fact, there's a little more to that. I've done a subtle little thing to this diagram so that when we get to another one later, I won't have to say, you know, I did that one wrong earlier. I don't know if you noticed, but there's something else about this that I did. I'll come back to that. So that's why suction cups work. A lot of other times, there are other times when you get suction. Has anybody ever used in science, I guess you wouldn't have biology, but maybe in middle school, did you ever use microscopes? So if you have two microscope slides, they're little pieces of glass. If you have two of them and they get wet and you stick them together really closely, they get stuck and you can't get them apart. But it's the same kind of thing in there. If you squeeze them together closely and you get rid of all the air inside, then there's pressure pushing here and pressure pushing there. So there's no way to pull those slides apart except to make them like a little transform boundary. You can slide them like this and separate them, but you can't pull them straight apart. Oh, and by the way, all the force that this thing generates, compare the size of this to my square on my arm. I don't know how many square inches this is, but I'd say it's probably 4 or 5. And every square inch has 14.7 pounds of force pushing against it. So if this is just 4 square inches, 4 times 14 would be 56. So that's why when I push it down to lift it back up, I have to overcome 56 pounds of pressure from the atmosphere. Okay, number 17. What happens if you fill a jar with water, cover it with a laminated card, turn it upside down? Explain why. So we're just going to do the simple solution here. Simple answer. Here's the jar. Really nice one. And this is the water inside. And here's the card. And I'm just going to say pressure, or air pressure, pushes the card up, preventing the water from falling. more to that. If you were in a college physics class, you would have to talk about, there's the weight of the water coming down, there's the air pressure on the outside pushing up, and then there's also the air pressure on the inside pushing down, and this pressure has to be stronger than that pressure, but we're not going to get detailed with that answer. All right. Now we're on to a new thing, and I think this is where something will come together for you. Number 18 says, quick review. What causes atmospheric pressure, the pressure in the air around us? So atmospheric pressure is different than pressure in a jar. So if I say atmospheric pressure, I just mean the air that's surrounding us. Does anybody know? Can anybody from home raise your hand and tell me what causes atmospheric pressure? I don't know if I should call on somebody. I won't. I'm not going to put anybody on the spot. So, atmospheric pressure. This is a really important question. If you learn nothing else, at least remember this. Atmospheric pressure is caused by the weight of the air, and that's not good enough right there. It's which air? Which air is causing the pressure around us right now? Is it the air below us, next to us, or above us? It's the air above us. It's caused by the weight of the air above us. So if you're a skydiver, for example, and you're halfway between the ground and the sky like this, it's the weight of all this air right here. If you think of a pile up, I don't know, I always say football, but I guess in football sometimes people pile up and jump on one. They tackle somebody and then more people tackle somebody, and sometimes people just pile on people for fun. But it's kind of the same thing. The amount of pressure you would experience in this pile increases as you go lower. So this person up here doesn't feel much pressure. The person right here feels pressure that's generated by all the people above him or her. So it's the same with air pressure. It's the weight of the air on top of you. It's the weight of the stuff on top of you. All right, 19 through 22. So we're going to recreate this diagram and then label the air masses, the cold air, warm air, cold air, either heavy or light. Use that weight to determine the amount of pressure beneath air masses. So along here we're either going to write high pressure or low. And then we're going to use arrows to draw the winds based on our highs and lows. And then you're going to use your knowledge of currents to fill in the rest of the diagram. So I'm just recreating this. This is going to be a lot like plate tectonics. And you could probably do a lot of this just thinking, oh, this is the mantle. But try it this other way. We're going about this a different way this time. I've got a few people here. I don't even know if you need the people, but I'm putting the people in. And this is position A and B and C. I'm not sure why I labeled the areas. All right, so first step, see if you can do this. Just colder air, warmer air, colder air. So each of those, either decide if it's going to be heavy or it's going to be light. And I just mean in comparison with one another. So what kind of air is heavy, what kind of air is light? All right, you should be done with that. This cold air, heavy or light? Everybody, just blurt it out. What's the answer? Light? No! What is... Cold air is heavy. I'm sorry. Don't feel ashamed. So cold air is dense. So if you, let me go back and I'll draw a Ziploc bag again. So here we've got this is supposed to be a Ziploc sandwich baggie. And if you have some air inside and you heat that air up, that air is going to move around really fast and the bag is going to expand. It's going to try to, or if it's a balloon, it's going to get bigger. This would be hot air. So if it heats up, it's going to expand. And then if you put it in and you cool it down, it's going to kind of shrink up. I don't know if this would be cold air. So in general, things expand when they get hot, and they shrink when they get cold. Because here the particles are moving around fast and pushing outward, and here the particles are moving around slowly. So if you were thinking that, I bet at least half of the other people were thinking that. So this should be heavy. Colder air is heavier. Really, more dense would be a better one, but I just want to write heavy for a specific reason. And then this, warmer air, that means it's lighter. Have you ever heard of a lighter than air balloon? Sometimes people call a hot air balloon a lighter than air balloon, which is what allows it to rise. And then the cold air, this is heavy. All right, so back to this. Atmospheric pressure is caused by the weight of air above us. You see where this is going? We've got heavy air, we've got light air, we've got heavy air. All right, so what's the pressure right here under the heavy air? High or low? So it's the weight of this air. The heavier it is, the higher the pressure. So this is going to be high pressure. And then if you have lighter air on top of it, it's not going to squeeze you as much. So this is low pressure. And here we've got more heavy air, so that's high pressure again. So the next step is to look at the H's and the L's and draw the winds. Can you tell which way the winds are going to go? Winds, if I review my notes here, moving air is wind, air moves from high pressure to low, wind blows from high to low. So should be going like this. So those are the winds, but there's the upper atmosphere. We've got to draw that. And the last step is to do that. Use your knowledge of currents to fill in the rest of the currents in the diagram. So now, just think, this is the mantle. We've got some currents here. They're going together at the bottom of the mantle. See if you can draw the rest.
So, Mr. Sam, can I ask you a quick question?
Mm-hmm.
I just thought we observed that if something is hotter, it's higher pressure when moving around.
Remember earlier I said, you know, I need to come back to this when I had the drinking bird, and I was saying that the butt is hot, and that creates heat and makes the particles move around, and that creates higher pressure down here, and that pushes the water up to the head, and the head is cold, so it has lower pressure. And then I said, so this is a good demonstration, but it's also kind of confusing based on what we're going to do later. So this is a sealed container, and this is a sealed container, but this, here I'm talking about atmospheric pressure. So out in the atmosphere, the air can expand really as much as it wants, or it could shrink. So it doesn't really, so lighter air, what it does is it doesn't build up pressure. If it expands, it would just sort of, it's going to move, well, let me finish my drawing. It's going to circulate like this, and it's going to mix in with this other stuff. So it never really builds up pressure. What it does is it's just going to actually make low pressure underneath it because it's light. So, and as I said that, I was just thinking this is even further confusing. But just to keep it really simple, it's just different. So if you think of pressures in a jar, it's not like pressures in the atmosphere. They're different. There's a different kind of reasoning. We've never talked about the weight of, when I say we heat up this jar, I've never said, look at the weight of all that air on top squishing the air down below. It's different reasoning entirely that gives us this area of low pressure and this area of high pressure. These are just caused by piles of air on top of them. And if you have a pile of heavy air, that's going to make higher pressure. And if you have a pile of lighter air, that's going to make lower pressure. So the wind is going to go from the high pressure to the low. And then after that, it's going to circulate like this. Yeah?
In the diagram, on the bottom, it goes from high to low, but on the top, it goes from low to high.
in the this. So Tommy has pointed out that up here, since this is all cycling around, it's going from high to low on this part, but now it's going back from low to high. And I'm really happy you asked that question, but I'm really kind of irritated because now I have to explain the complexities, and I didn't want to get into them, but it's okay. So don't all be confused about this. Just remember that part. If this part makes sense, that's fine. So as you go up into the sky, what's happening to the air pressure? As you go higher, is there more air on top of you or less air on top of you? Less. So even though I've written low pressure here, the pressure up here is going to be even lower, because this is low pressure because there's light air on top of it. But right here, this would be, I would just have to say, really low pressure. Because there's very little air on top of that. So that would explain why it would go up. Now, there's this is really complicated. We haven't even really gotten into this. Well, I guess we have. Okay, we can do this. This is Tommy's fault. So picture some air, and it goes up. And as it goes higher, there's less and less pressure around it. So if I show a bubble, I'm going to show you all the air squeezing it. As this bubble goes higher, is there going to be more squeezing it or less squeezing it? Less. So if the squeezing is less, what's going to happen is the bubble is going to expand. I don't know if you've ever seen artist drawings like this, but as bubbles rise up, they get bigger. Has anybody ever noticed that? People will draw bubbles rising off the bottom of a tank, and they show them getting bigger. They really do get bigger, and they get bigger because there's more pressure down at the bottom and less pressure at the top. So think back to when we're making clouds in a bottle. If you squeeze something, does that make it hotter or does that make it colder? That heats it up. Squeezing things heats them up. Letting things expand cools them off. So as this bubble is rising and expanding, it's also cooling off. And that's what makes clouds form. We were going to get into that later. So as this rises up, it encounters less pressure, and that allows it to expand. That cools it off. So it becomes colder. It also becomes less dense. So this warmer air, as it's rising, it actually gets colder. And when it spends more time up in the top of the atmosphere like this, farther away from the surface of the earth where the sunlight hits, it cools off, cools off, cools off. So this is kind of like a lava lamp. It rises up, becomes less dense, cools off in the process, stays away from the earth, gets even cooler, and when it's cold and heavy enough, then it starts to sink again. And when it sinks, just the opposite happens. So as this sinks, it's going to go from maybe a big bubble of air to a smaller bubble, to a smaller bubble, to a smaller bubble. So it's going to get compressed. And when you compress it, what does that do? Cool things off or heat things up? Heat things up. So up here, what we really have is some super cold air, but all right, so this is such a good question. I've never really thought about it much until now. When this air sinks, it's not just the pressure difference that's pushing it. It would also be gravity is pulling it down. So when it gets heavy enough, it's also got gravity working with it. So the way that I can reconcile this going from an area where there would be lower pressure to pressure is that it's not just the pressure difference that causes it to move this way, but it's the fact that its weight is pulling it down. So that's what can get it down to here. So I can explain high to low pressure on equal elevations. That's the way wind moves. That's the part you need to remember. That's the simple part. And then I can explain this rising because it actually is going to go to a place where there's lower pressure. In fact, we're going to show in a second that everything is being pushed up all the time, even you right now, although you're too heavy to float. And then this is going to, maybe this movement over here, from there to there, I don't know, this one's kind of, I'm getting a little stuck on that. I'd have to think a little bit longer to explain this from a pressure standpoint. But hopefully I added a little bit of clarity and complexity, and that was good. That's a good. This is a good lead into what we're going to talk about later, which is to say, as air rises, it goes up, it expands, and it cools off. And when it cools off enough, then you get clouds. So rising air creates clouds, and then if you have air sinking, the air gets compressed on its way down, and that heats it up. So that's what gives you dry weather. Rising air is wet, sinking air is dry. That's going to be a huge thing later on. Hopefully your notes don't look like mine. Hopefully you've just got mostly, like, the thing I want you to remember, just this is the thing to practice. Heavy air really is, colder air really is heavier, so it sinks. It's dense. Lighter air really is, or warmer air really is lighter, it rises, and this sinks. And the cold stuff, since it's heavy, creates high pressure below it, and this creates low pressure below it, and these winds really do go from high to low pressure. What happens up there? That gets a little more complicated. But I'll try to figure it all out. Maybe I'll make a nice video for anybody who wants to understand more. So this was my 19 through 22. And then I've got all these piles of people and other stuff that are kind of irrelevant in my notes. All right, almost done. Buoyancy. So this is something I think I mentioned a minute ago. Buoyancy is caused by pressure differences. This isn't super important for understanding weather, but I think it's important because Tommy will ask me about it, even if I don't tell you about it, so I better tell you about it. So helium balloon. A bubble, anything that floats knows which way is up. Like if you let go of this balloon, it'll go up. We've talked about things that are less dense rising and things that are more dense sinking, but we've never really talked about why and how they know. This doesn't have a brain, so how does it know which way is up? What makes it, how does it choose to go whoop? People who have brains sometimes get disoriented underwater, and what do divers do to figure out which way is up? They blow some bubbles, and then you follow them. So the bubbles know, and the question is, how do the bubbles know? So we'll draw a diagram to show how bubbles know which way is up. That's really another way to rephrase this question. This could be a bubble, this could be a balloon, could be whatever. This is the helium balloon. So the way they know is by the pressure. So right here, compared to right there, I'll just label this A and B. Where's the pressure stronger? At A, or is the pressure stronger at B? Here's the ground. Here's the poor little kid long-legged kid, long-necked kid, who let go of the balloon. There's the balloon rising away. Where's there more pressure? At elevation B or at A? B. And the reason there's more pressure at B is because there's more air above B, and there's less air above A. And it's the weight of the air above us that causes pressure. So the lower you go, the more pressure there is. The higher you go, the less pressure there is. Pressure pushes in on things from the side. I'm going to draw a bunch of arrows representing air pressure pushing from different sides. Which arrows should be the longest? there's more pressure. The lower you go, the more pressure there is. The higher you go, the less pressure there is. So if you think of these as a bunch of people, all of them having some sort of tug of war, except it's backwards, it's a push of war, and they're trying to push this balloon, and you've got the stronger pushing people on the bottom and the weaker pushing people on the top. Which way is it going to go? It's going to go up. So I'm going to say pressure pushing up on the bottom is stronger, and the pressure pushing down on the top is weaker. And there's a name for this, and that's what 24 is asking. The name for this upward force is called, and it begins with a B. Does anybody know what it is? Buoyancy. It's got a weird spelling. I don't care if you spell it right. B-U-O-Y-A-N-C-Y. Buoys are spelled like that. I don't know if the name buoy came from buoyancy, or if buoyancy came from buoys. Buoys are little floats that people use in association with boats. And number 25 asks, does everything around us experience buoyancy? And the answer is yes. Everything experiences buoyancy, even you right now. Well, everything that's in air or water, everything in a fluid. If you're in the vacuum of space where there's no air, then there would be no buoyancy. But you'll never be in a place where there isn't any buoyancy. And then if, for example, if I draw myself, this is my self-portrait, and I draw the pressures pushing on myself, I'm just going to draw the pressure from the top and the pressure from the bottom. And by the way, unless I'm wearing suction cup shoes, there's always air under me pushing me up. If I put on suction cups on my feet, then this pressure is going to hold me down and there will be no pressure pushing me up. But normally there's more pressure pushing me up than down. Why don't I float away? That's happening right now. Like, if I let go, buoyancy is pushing me up, but I'm not floating away. I'm going to combine number 26 and number 27. So the reason, why does a rock sink and a cork float? They both experience buoyancy. What's the difference? What's holding the rock down that's not holding the cork down? What's a force that's pulling us down that's counteracting buoyancy? Gravity. So if gravity is stronger than buoyancy, you sink. If gravity is weaker than buoyancy, you float. And that's the difference between things that float and sink. We all have buoyancy, but if we have more weight than buoyancy, then we sink. So I'm going to just make a little note here. I sink in air because my weight is stronger than buoyancy. Now, do you think that's true in water? If I got in water, do you think I would sink or would I float? Most people float. I actually sink. It depends. If I get a really, really, really full breath of air and I wear my Chaco sandals in the water, I can almost float. But if I take my sandals off, I sink, even with the full breath. So the very last one, dense things sink because they have more weight than buoyancy. bubbles, with helium balloons, they all have more buoyancy than they do weight. And that was a really long time. People at home are probably all snoozing. I can't hear them snoring, but they're muted. So, the homework is just to review these notes. And I'm going to circle some of the ones I think are most important. Those are the ones I'm really going to key in on. So, this, number 3, super important. Number 5 is super important. Being able to do something like number 6, everybody ought to be able to do that. Number 12 is a real big one. Number 13, I'm going to ask some people about ears. And for example, what would happen if you went from the top of Mount Mansfield suddenly down to like, Underhill? So you went down the mountain real fast. What would happen to your eardrum and why? I might ask you a question like that. I think I will ask you, I don't know, 14 and 15? Sure. These are not so important. I'm just going to write, not a huge deal, but they're good to know. Why does the suction cup stick to glass? I think that's something everybody should know. I'm going to ask people about that. And then I'm definitely going to have, so 18, I think that's a repeat of number 12. 19 through 22, I'm going to have a new diagram like this, and I'm going to have some of you help me draw it. And 23 and 24. So just to repeat, the ones you should really be ready for me to ask you about are 24, 23, 18 through 22, 16, 14 and 15, 12 and 13, 9 I circled from earlier. I think you all know that anyway.